Everyone, very good morning. So I will today read this paper while uh, riding my cycle. You can see currently I am riding my cycle. Okay, you can see. Let you see. This is my cycle, and I am riding on IT Jodhpur road. You can see here, very beautiful morning, and it's very good to read paper while riding it. Okay, so without any wasting time, I will what I do. I will read this paper. Okay, so start reading it. So robotic characterization of markerless hand tracking on Meta Quest Pro and Quest 3 virtual reality headset. Okay, so starting from here, first I will introduce the authors. The authors are Eric Gordon, William Stedman, and Matthew K. XJ Pan. Okay, so abstract. First I will show you a figure. This is a figure of a fully integrated markerless hand tracking characterization system with which combines the VR HMD, that is MetaQuest Pro here, as you shown here. Okay, this is MetaQuest Pro, that is here. Okay, and KUKA LBR IIWA 7 R800. This is a robotic manipulator and custom hand model and effector. So starting from the abstract, so markerless hand tracking has become increasingly common on commercially available virtual mixed reality headsets to improve the naturalness of interaction and immersivity of virtual environments. However, there has been limited examination of the performance of markerless hand tracking on commercial hand-mounted displays. Here we propose an evolution methodology that leverage a robotic manipulator to measure the positional accuracy. Okay, so jitter, latency of the systems, and provides a standardized characterization framework of markerless hand tracking. We apply this methodology to evaluate the hand tracking performance of two recent mixed reality devices from Meta. There is the Meta Quest Pro and Quest 3. Okay, results demonstrate the influence of proximity to the headset, rotation of hand, and joint selected as the tracking feature on the hand tracking performance. We found that hand tracking error and jitter were lowest for both headsets in condition where knuckle was the tracking point compared to the fingertip. Okay, so regarding positional accuracy in best performing condition, the Quest Pro outperformed the Quest 3 with 1.22 centimeter. That's the cost difference. Quest Pro definitely more better than Quest 3. It will definitely outperform with 1.22 centimeter of average error compared to 1.73 centimeter. The opposite result was true considering jitter, with result of 1.77 centimeter and 1.17 centimeter for the Quest Pro and Quest 3. Okay, respectively, and we found latency highly variable for Quest 3, that is 15.8 to 229.2 millisecond, and Quest 3 14.4 to 220.5 millisecond. This works provides a testing framework for highly systematic, repeatable performance measurements of markerless hand tracking system embedded in headsets. Okay, so index terms are hand tracking, and robotics tracking performance characterization in virtual reality, and hand-mounted displays. Okay, going to start the paper now. Introduction part. Okay, markerless hand tracking is becoming a common feature on virtual reality. Okay, hand-mounted displays HMDs is present on current generation Meta Quest and HTC Vive products. Hand tracking, as opposed to controller tracking, allows the user to interact with the virtual environment without needing handheld controllers. This ability produces more realistic and meaningful interaction with virtual environment and can put the user in a more active role within the experience. VR interaction based on hand tracking are becoming more commonplace for VR applications such as physical therapy and robotic teleoperation. Okay, this is given by, again the authors names are given: Eric Gordon, William Stedman, and Matthew K. XJ Pan. Okay, they are from Queen's University. Email IDs are given. That's good. Okay, now continuing the paper here. In these and other applications, An understanding of hand tracking performance is essential to users, practitioners, and developers to understand their limitation. Hand tracking is still a developing technology within the VR domain as limitation of tracking location and performance persist. The technical difficulty of markless hand tracking over the traditional approach of using a user hold instrumented controllers necessities computer vision methods for processing inputs, and that's thus leading to lag and added noise that may hinder the overall performance of the system. Without an understanding of hand tracking performance, there can be a mismatch between the expected and actual accuracy of hand position data, which may be determined to the user experience. For example, hand tracking fidelity is critical to virtual and mixed reality experience that merge real and virtual world in accurate hand tracking, while motion capture is needed to allow a user to catch a ball while immersed in VR. Also in article reference number 19, markless hand tracking is used within virtual experience to evaluate and classify tremors in the hands of patients with Parkinson's disease. Sufficient hand tracking accuracy is required in evaluating tremors to ensure highly detailed data can be captured. Here we focus on this need to characterize the markless hand tracking performance and present a process of doing so. In this work, we describe a robotic testing methodology. Our testing setup is shown in figure 1 to provide standardized testing of markless hand tracking performance. Using this process, we obtain measurements of 1 minute. I should off the notification. It's really annoying to have the set sound notification sound. What I can do is D&D mode, put in D&D mode, do not disturb mode. Fine, it's okay. Now continuing the paper. Here, so I was here tracking performance and present a process for doing so. In this work, we describe a robotic testing methodology. Our testing setup is shown in figure 1 to provide standardized testing of markless hand tracking performance. Using this process, we obtain measurement of positional accuracy, jitter, and latency of two commercially available VR HMDs, the MetaQuest Pro and Quest 3 SD HMDs. We possessed that our HMD characterization will be foundational step toward understanding, addressing, and improving markless hand tracking for VR and other systems, improving the immersivity of future HMDs. You can see here. So background: markless tracking. While it is clear hand tracking can be beneficial to user experience in VR, markless tracking is difficult task that present many additional challenges compared to traditional controller tracking. Controllers within VR systems are integrated with additional pieces of technology such as inertial measurement units IMU, and infrared lights to enable sensor fusion and optical tracking to enhance performance. Markless tracking, on the other hand, inherently does not rely on any augmentation to the tracker object and must perform its tracking from an outside perspective. This technique often required computationally expensive computer vision algorithm and demands highly detailed image input. In addition to the use of more limited technology for tracking, the hand is difficult object to track. The hand has more than 20 degrees of freedom, and can experience rapid motion up to 5 meter per second, and 300 degree per second, radiation, and experiences of self occlusions. These factors often result in decreased performance compared to traditional controller tracking. So which takes the form of lag within the user experience and highlight the critical need for mitigation strategies in the event of tracking failure. Common techniques of markless hand tracking use RGBD, and infrared cameras to obtain the information about the hand, necessary for tracking. In recent years, learning techniques have leveraged neural networks to train algorithms which have improved hand tracking performance. One example of this includes the work by Han which serves as the default for hand tracking on MetaQuest headsets. Okay, this approach uses 4 monochrome cameras to provide multiple image inputs at each tracking frame. An efficient convolution neural networks simultaneously localize and classifies the hands within the images. A motion prediction step is also present in this algorithm to help minimize system latency. The final step predicts 21 key points across the hand to provide detailed information on the anatomical feature of the hand. So, tracking performance. Previous studies have evaluated the effects of latency within human machine interfaces. The knowledge is foundational for performance analysis in VR. You can see Lee studies 17 explored the effect of delays in network human machine system. Results showed an average of discrimination threshold for visual delays to be 50 ms and a greater requirement of simultaneously which when haptic information is involved. So J et al. Also explored the effect of visual lag in a reciprocal tapping task, determining that the decimal threshold of visual lag is 94 milliseconds. This results represents performance degradation with increased latency under a simple visual task, which may only become more severe and or sensitive in the complex interaction experience within VR application. Significant correlation between latency and other factors have also been shown in VR, such as decreased bandwidth 20, motor performance 32, and body ownership, and including cyber sickness. Okay, so in words, now with increased visual delay, okay, and these affect our many aspects of user experience in virtual environments. With latency of commercial HMDs must be considered when developing virtual experiences to produce desired outcomes. Prior work focusing on performance analysis of VR environments, VR systems, includes studies on room scale tracking, controller, and hand tracking. Okay, room scale tracking characterization are generally performed with the devices that use lighthouse tracking system as a performance. Okay, then carry with proximity of to base station. Robotic manipulators can carry with proximity to base station. Robotic manipulators have been used in VR device characterization due to their ability to establish repeatable motion and potential to establish ground truth reference. Motion capture technology can also establish ground truth and ground truth reference and is efficient for use in room scale analysis. Okay, so now Maijera et al. Evaluate two hand tracking variable and vision based system for use in teleoperation and virtual manipulation. The devices studied in this work have the drawbacks of requiring additional hardware to accompany a user's VR HMD. As markerless hand tracking technology is relatively new is commercial VR devices, there is a limited prior work in this area. To our knowledge, Abdul Kalarim represent the only markerless hand tracking characterization of a commercial HMD. In their work, participants were outfitted with relative markers on their index finger to compare motion capture data to the hand tracking for the MetaQuest 2. The characterization consisted of target reaching and hand opening and closing tasks to produce results of delay, referred to latency in our work, static potential error, path offset, and angular error of the index finger. Their work produced a single average delay result of 45 milliseconds by determining the time difference in velocity peaks between data from two measurement systems. Additionally, they found an average static potential error of 1.1 centimeter and proximity to the HMD influenced the tracking error. Our work builds upon the markerless hand tracking methodology presented by Abdul Kalarim by developing a more rigid set of tests that uses a robotic manipulator to characterize markerless hand tracking and more recent HMDs. The objective of the study are threefold. design a repeatable, extensible testing process that enables robust characterization of markerless hand tracking performance in terms of latency, pause accuracy, and pause jitter. Characterization characterize the performance of two current generation HMDs equipped with onboard markerless hand tracking, the methodologies Pro and methodologies 3. Using this testing process, understanding the limitation of markerless hand tracking on these devices in terms of the observed matrices, and discuss their impact on implementing application that benefit from hand tracking. Okay, now next overview of framework for markerless hand tracking characterization. We observe a comprehensive framework to systematically evaluate the performance of markerless hand tracking system in VR HMDs by combining robotics, motion capture, and virtual environment rendering. The framework enables precise, repeatable assessment of key matrices such as positional accuracy, jitter, latency. It addresses the need for standardized evaluation methodology to ensure reliable comparison across devices and conditions. The framework, 1 minute, it will be better from this. Okay. Now starting with the framework integrates several key components shown in figure 2. Okay. A robotic manipulator, we use a KUKA lab IIWA 7R800, perform repeatable and precise movements to simulate hand motion, while a 3D printed hand model with retro-reflective markers provides standardized and accurate ground truth reference points. The Vicon motion capture system delivers sub-millimeter precision in tracking the HMDs like methodologies Pro and Quest 3. All subsystems, including the virtual environment rendered in Unity 3D, are synchronized through the real-time communication protocols to ensure consistency. Okay, consistency is important here. The framework evaluates performance through the 3 tests. The static performance test measures accuracy and jitter under a stationary condition by positioning the hand model to various points within the tracking volume. The dynamic performance test assesses latency during motion, calculating matrices like call start and constant velocity latency by moving the hand along predefined trajectories. The motion to photon latency test measures the end-to-end delay from hand motion to visual representation on the HMDs, offering insights into the user perceived latency. The framework introduces several innovations, including the use of robotic precision for repeatability and the evolution of multiple matrices for a holistic performance analysis. Its modular design allows for future, you can see here the diagram, the figure 2, allows adaptations such as expanding the testing volume or incorporating additional matrices such as complex gesture by way of an articulated hand model. By standardizing the characterization of markerless hand tracking system, this framework provides a foundation for developing more reliable and immersive VR technologies. Okay, so you can see here this is a diagram of a markerless hand tracking characterization framework developed in this work. The framework integrates a robotic manipulator and virtual reality subsystem to assess tracking performance through 3 tests, while corresponding result outlined for each. Okay, the test results are given. 3 tests for each. System design for 2. Robotic manipulator, 2 system design. Robotic manipulator, the replica hand, motion capture system, real-time control, and ROS2 communication. And virtual reality, heads-mounted display, virtual environment rendering, and markerless hand tracking algorithm. Okay, now the performance evaluation. Test 1, static performance, average Euclidean error, okay, and jitter. Dynamic performance, warm-up duration, and cold start latency, okay, and constant velocity latency, and motion to photon latency. Motion to photon latency is already there. So experimental setup. The experimental setup we developed in this work was for testing hand tracking performance, combines several subsystems. So first starting from the VR HMT's motion capture system, robot manipulator, and underlying communication system that allows data to transfer between the aforementioned subsystems. Okay, and virtual reality and head-mounted displays. First, this is given. The two HMDs evaluated in this study are MetaQuest Pro and MetaQuest 3, and MetaQuest HMDs are selected due to their popularity influence in the VR community. Okay, and their onboard markerless hand tracking capabilities. The MetaQuest Pro features the Qualcomm Snapdragon XR2 Plus Gen 1 processor with 12 GB of RAM and 5 integrated cameras to facilitate tracking. In MetaQuest 3 is more advanced than MetaQuest 3, the MetaQuest Pro. You can see the RAM 12 GB and processor is also great. It's Qualcomm Snapdragon XR2 Plus, that's great, Gen 1 processor. So MetaQuest 3 features the Qualcomm Snapdragon XR2 Generation 2 processor. The processor is the advanced here with 8 GB of RAM and 4 integrated cameras, while in MetaQuest Pro 5 integrated cameras. And in Quest Pro you can see integrated camera with a depth sensor to facilitate tracking. The virtual environment used for testing was developed and rendered using Unity 3D game design, a Unity 3D game engine on a Windows 11 x64 laptop, AMD Ryzen 7 6800H 3.2 GHz and 16 GB RAM, NVIDIA GeForce RTX 3050T. This is the essential system required for rendering it very well. The virtual environment included a minimalistic blend of neutral color to create a scene of low complexity to minimize the rendering workload. All testing was done with HMDs tethered via a USB 3.0 wired connection to laptop rather than running the HMDs in standalone mode to limit latency in data transmission and collection. Hand tracking post data was accessed through Unity's XR interaction toolkit, you can see, and transmitted at a rate of approximately 90 Hz, and transmission occurs with Unity's mono behavior update function that is variable and depends on system performance. Okay, 90 Hz was chosen as the refresh rate as it is highest set refresh rate available between the pair of headsets. So you can see here. So now robotic manipulator. We use a robotic manipulator for our study to produce repeatable motion essential for comparison across trials and hardware. In our experimental setup, a KUKA LBR IIWA 7R800 robot manipulator horizontally mounted on a pedestal was used to mimic the kinematics of human arm, precisely perform the stationary and dynamic positioning required for this characterization. The robot was position controlled and received post data in real time with a loop rate of 1000 Hz using KUKA's proprietary fast robot interface FRI. The robot was controlled via a desktop machine Intel Core i7 14700 4.2 GHz 32 GB RAM with Ubuntu 22.04 real-time kernel. Software for driving testing behaviors on the robot was developed upon the robot operating system 2 ROS2 and humble Havak builds version with this version is given. LBR FRI ROS2 stack being used to provide ROS2 package for FRI communication with the robot. A custom mechanical support structure was designed to fix the headset location and reinforced to ensure vibration through the structure were minimized. Replica hand. So replica hand, since this work focuses on hand tracking performance, externalized hand was fabricated to provide consistency across all testing trials. An open source hand model produced through an EVA optical scan was used, which ensured high accuracy and clear anatomical features, okay, which were required for key point matching on the virtual hand. This model was further modified to allow for 6.4 mm spherical reflective markers to be placed at each anatomical joint on dorsal and palmar side of the hand, as well as at each fingertip. The tracking location of each point was midpoint between corresponding dorsal and palmar side markers. The model was 3D printed using PLA material on a FDM printer as shown in figure 3. This technique provides provided on FDM printer as shown in figure 3. This technique provided high confidence in defining ground truth location in relation to the corresponding key point of the VR hand tracking. A hand now see a hand was fixed to the manipulator's end effector and secured consistently for each trial. Pilot testing demonstrated no degradation in landmark identification or hand tracking capability due to added marker and filament color. The combined system is shown in figure 1. You can see the figure 1 again, how it is done. Okay, now motion capture system. So we use retro reflective marker based motion capture system Vicon Vero V version 2.2 to provide an efficient ground truth reference for our VR. You can refer the link unity.3d.com packages, all these links, kuka.com, grabcat.com, and everything, the users in this project, in this research paper, all the links are here, reference links are here. Okay, so continuing the paper now. Okay, so hand tracking data to be analyzed, the system was used in tandem with software Beacon Tracker. The version is here. That was run on Windows 11 x64 system, Intel Xeon W213 3.6 GHz, and 16 GB RAM to provide tracking of retro reflective marker constellations. This system produces sub-millimeter error and low camera latency of 3.6 milliseconds. So communication, the synchronization of all subsystems was coordinated on robot control system, facilitating the manipulator control to synchronize efficiently. The VR and motion capture system delivers serialized data using Google's protocol buffer framework through high-speed UDP over Ethernet. This minimizes system latency and the influence of network traffic. Registration between measurement frames to ensure proper comparison of data between the motion capture and VR coordinate frames. A registration process was completed. This process involved taking measurement of the same anatomical feature on the hand over 30 unit points in both frames. A least squares approach was used to produce a homogeneous transformation matrix, okay, where the two sets of values were adjusted around their respective means that, and the singular value decomposition was taken. The methodology that was used here, our testing methodology examines the markerless hand tracking accuracy, jitter, and latency for both the MetaQuest Pro and Quest 3 through the 3 tests: a static performance test where hand tracking performance is evaluated when the hand is not moving, a dynamic performance test where hand tracking performance is evaluated as the hand is moving, and a motion to photon latency test that measures the delay between the hand motion and when the motion is displayed on HMD. While other characterization may only report single value results for performance factors, this work aims to provide detailed results that contain multiple evaluation for both position and latency performance. This will produce a more comprehensive understanding of hand tracking performance and is currently unavailable. So test 1, static performance. So this test evaluates hand tracking performance under static condition, removing the influence of latency on measurement accuracy. This scenario represents the optimal tracking condition as temporal factors are eliminated and hand pose remains constant between frames. Okay, this consistency provides a table perspective to the HMD cameras, simplifying the identification step in tracking algorithm. The static test condition is crucial for understanding the upper limit of tracking performance and is particularly relevant for precise interaction in virtual environments. So Adel Karim highlighted the influence of hand proximity on tracking error. This motivates the static testing to be performed across a three-dimensional testing volume defined by the lateral and anterior proximity to the HMD. For each level of consistent vertical proximity, there are 7 best positions as shown in figure 4. Table 1 details the lateral and anterior proximity to the HMD and the yaw rotation as an offset form from the pose with fingertips facing forward for each position. Position 1 and 4 and 6 were adjusted through yaw rotation to recreate more natural hand position that would be found using an anatomical accurate manipulator. These positions, the positions were chosen to evenly cover a quarter of circular testing area with radius of 0.4 meter and centered on the first position. Okay, you can see here the positions: 1 0.1 meter lateral offset and vertical offset 0.15 and yaw rotation 45 degree, and for each position you can see the simultaneously respective lateral offset and vertical offset and yaw rotation. Okay, for last one you can see 0.1 and vertical offset, the lateral offset is 0.1 meter and vertical offset is 0.5 vertical offset meter, and yaw rotation is 0 degree. Okay, so this static test position for each consistent vertical test of 3-dimensional testing volume defined by the lateral and anterior proximity to the HMD and the yaw rotation. Okay, the 3 vertical levels were defined to extend the testing volume in third dimension. Okay, the first level is situated closest to the HMD. Okay, recording will stop, auto stop. Okay, the following. So the first level is situated closest to the HMD was position 0.1 meter below eye level. The following 2 levels were position 0.2 meter and 0.4 meter below the first, creating a testing volume. There is quarter section in 0.4 radius and 0.4 meter tall cylinder. Similar to the adjustment in yaw rotation of the hand across the 7 position, all the rotation on the first level were pitched upward. The first 3 positions were pitched 45 degree upward from horizontal and the rest were pitched 22.5 degree. This again ensures that the hand is positioned in automatically realistic position at elevated levels and provides greater line of sight visibility between the HMD and track index finger feature. As the manipulator to the left of the HMD was tested, the testing region was defined solely to the left of the HMD, as the majority of left-handed interaction within VR would occur in this region, giving it priority over extended workspace that would rarely inhabit a left-handed interaction. Okay, interactions within VR and would occur in this region, giving it priority over extended workspace that would rarely inhabit a left-handed interaction. We assume that the performance is systematic across the medial lateral plane of the headset, allowing the results of this work to be extended to a right-handed model in its corresponding most relevant region as well. To further improve the robustness of this test, 7 rotations were applied to each best position before moving to the next, as hands were rarely you can see here as hands were rarely sit flat across interaction within a virtual environment. That applied rotation will ensure the result within the test considered included an identified rotation, no keep and ulnar radial revision of 15 degree, flexion and extension of 45 degree, and supination and pronation of 15 degree. The flexion and extension conditions were given greater rotation as they required to have a sufficient change in hand profile from the perspective of the HMD. With 7 rotation at 7 positions per level, this total 147 unique testing points. For the first test, the tracking performance of 2 anatomical features of the hand were also compared. So starting it, okay, I have to change the location. To further improve the robustness of this test, 7 rotations were applied to each best position before moving to the next, as hands were rarely sit flat during interaction within a virtual environment. You can see here, the applied rotation will ensure the results within the test considered the influence of rotation and hand tracking performance. The rotation included in this order denoted 1 through 7. An identity rotation to keep hand at a base position, ulnar and radial deviation of 15 degree, flexion and extension of 45 degree, and supination and pronation of 15 degree. The flexion and extension conditions were given greater rotation as they required to have a sufficient change in hand profile from the perspective of the HMD. With 7 rotation at 7 positions per level, this total 147 unique testing points. For the first test, the tracking performance of 2 anatomical features of the hand were also compared to understand, you can to understand optimal tracking location on the hand. The anatomical features selected were the index finger, okay, and tip. This is distal phalanx and cuneical beta carpophalangeal joint. Okay, I was able to pronounce, but meta carpophalangeal joint. The index finger was selected as it is generally the most medial finger during interaction in VR, which provides the clearest line of sight and therefore the best tracking potential for the HMD cameras. Okay, the tip of the finger cuneical were the two anatomical feature on the index finger chosen within this characterization, as they provide clear landmark on the hand. You can see the static performance testing region for each level used in test 1. You can see here. Okay, this first, second, third, fourth, and fifth. This is fifth, sixth, seventh. Okay, you can see here. Left hand. This is left hand. Okay, the features such as palm and wrist were excluded due to their difficulty in aligning these features on the model hand to that of virtual hand. We are unaware of any other work that compares the tracking of different anatomical features on the hand for commercial HMDs. At each unique point, measurement was delayed for 1.5 seconds to ensure the hand tracking latency effects were nullified. Once the delay was completed, 50 measurements were taken from both the ground truth and VR data at a sampling rate of 90 Hz, and VR data transmission rate as this was combined slowest update to ensure unique measurements at each sample. For each testing point, two results were calculated: average Euclidean error and sample to sample jitter. Average Euclidean error is computed by taking the mean of 50 measurements at each point from both the motion capture system and markerless hand tracking of the headset. The homogeneous transformation matrix obtained from registration is then applied to convert the position of the same coordinate frame. The Euclidean distance between 2 points can then be calculated to produce the average error. The Euclidean error is an important metric for characterizing tracking performance, as separation from ground truth is a true indicator of the deviation from desired performance. Jitter represents the magnitude of frame to frame jumps in subsequent stationary measurements. The sample to sample jitter provides a measure of the noise experienced by the measurement system. High amounts of jitter also produce negative effects by creating less natural hand motions that can reduce social presence and make an interlocutor less comfortable in a social virtual interaction. This metric is calculated by taking the root mean square of the 50 measurements at each unique testing point. Equation 1 outlines the RMS calculation, where n is the number of measurements, 50 in our case, and delta mi is the difference in samples I and I plus 1. Test 2 dynamic performance. This test evaluates the hand tracking performance under dynamic conditions to evaluate the latency of markerless hand tracking on each HMD. Latency refers to the time delay between ground truth motion when the corresponding motion is detected by the measurement. So you can see here, one second, system, since our ground truth is operating at a refresh rate of 240 Hz with a 3.6 millisecond camera latency, these potential delays can be accounted for in our results. The maximum latency of the ground truth camera latency with an additional one full cycle at 240 Hz will be 7.7 millisecond, which can be considered in each result in test 2. Okay, from the user perspective, within a VR application, latency encompasses both the temporal and positional error in a dynamic interaction and therefore provides essential information on hand tracking limitation. Okay, latency is also an important factor for embodiment of virtual avatar and affects the ability to perform dynamic contextual interactions such as non-verbal communication. 12 constant velocity trajectory of hand are defined across 3 vertical levels at 0.3 meter and 0.4 meter and 0.5 meter below the eye level of the HMD. Okay, the testing volume was modified from test 1 to facilitate both joint velocities across all trajectory. From initial testing, trajectory on vertical levels about 0.3 meter below eye level could cause certain manipulator joints to have extremely rapid motion, which had a greater uh, difficulty following the desired linear trajectory. The manipulator also occulted the joint hand in some position at higher vertical levels, which did not facilitate consistent tracking. Therefore, trajectory on vertical levels above 0.3 meter were not included in this test. At each vertical level, 4 trajectories were defined, 2 at distance of 0.3 meter and 2 at a distance of 0.4 meter. Okay, in the anterior direction from the HMT. Out of each pair trajectories at a unique vertical and anterior position, one moves the hand from left to right, and other from right to left. Okay, each trajectory expanded 0.3 meter and had steady state velocities of 0.2 meter per second, with constant acceleration and deceleration period lasting 10% of the total trajectory. Okay, the acceleration and deceleration, you can see, periods were established to mimic natural hand motion and to minimize the vibration experienced by the system. During each trajectory, data was recorded from the ground truth and the VR system at the highest update rate available, ground truth to 240 Hz. Okay, this produced potential for information from each measurement frame across the full trajectory. Data recording begins 0.25 second, okay, 0.25 second before the start of each trajectory and ends 1 second after the end, ensuring the full trajectory could capture by both measurement system due to expected latency of the hand tracking. The chronicle is selected as a tracking feature of this test due to better tracking performance than fingertip in test 1. Okay, you have seen. This helps minimize the effect of positional error when trying to isolate for tracking latency. Okay, while other studies only report a single value of VR system latency, in reality, latency varies dramatically throughout different phases of motion. Variable performance throughout motion can be attributed to motion prediction step common in modern hand tracking algorithm. This variability was initially confirmed in our pilot study, as latency was highest at motion onset and become minimal at steady state, but a more thorough analysis is required that time. This test will therefore produce 3 matrices to provide a complete evaluation of hand tracking performance across the entire motion. Okay, cold start latency, motion prediction, warm up duration, and constant velocity latency. So cold start latency refers to time delay of onset of motion. This measure removes the effect of motion prediction as the hand begins the trajectory stationary, and represent the worst case tracking condition within our test. Since both our measurement systems experience noise, using a simple motion onset detection technique would not be viable. Okay, and this demonstrate the war button demonstrate the particularity of an outlier detection technique based on the median absolute deviation that is made to detect motion onset in a VR system. This technique will be used for ground truth and VR hand tracking data to detect time of motion onset of each trajectory. The corresponding delay between the ground truth and VR hand tracking motion onset is our cold start delay latency. The MAD detection technique is shown in equation 2:18. Xi minus m and b dot mi, or xi minus mj xi, that is greater than plus minus c. This technique relies on median function m, constant b, and c, and window of sample x. Not the c equal to 3 is a conservative selection, and b equal to 1.48826 is generally used as it is tied to the assumption of normality in the data. These constant values will use in our analysis. In preliminary test, a window size of 60 samples was shown to have a strong performance if the VR detection point was ever before the ground truth detection, indicating a false positive, as the VR hand tracking typically succeeded the ground truth motion. The window size was increased by 10 until this was no longer the case. The lengthening of window lowered the impact of high noise features within a stationary measurement to help improve detection in some cases. As the stationary start removes the influence of motion prediction will begin to influence performance once the algorithm has adequate time to evaluate the motion. As noted by Warburton, there is a warm-up duration for the motion prediction to take the effect and will cause the experience latency to decrease from motion onset until a steady state condition is reached. To determine this motion prediction warm-up duration, latency will be determined across the entire motion. First, the ground truth and VR trajectory will be aligned using the corresponding detected motion onset points from the called start latency analysis. From motion onset, each ground truth measurement will be projected forward in time along the VR trajectory until a matching position is reached. The time difference between the corresponding ground truth and VR measurement will be the latency at the specific ground truth time. This process is repeated until 80% of the ground truth trajectory is evaluated to discount the deceleration phase of motion. For phase of the motion with latency, our most of the trajectory determined. The warm-up duration is defined as the time from motion onset from latency to become 5% of the final latency value within the trajectory. Once the warm-up duration is found, the constant velocity latency can then be determined by averaging latency values from the warm-up period. The period used to determine constant velocity latency represent the best tracking condition and analyzed in the test as the motion prediction is in full effect and trajectory is outside its acceleration field. The now test number 3, motion to photon latency. While the first two tests provide an in-depth evaluation of hand tracking, okay, you can have seen before, performance across static and dynamic conditions. Another key delay to consider within VR system is the motion to photon latency. Okay, the motion to photon latency encompasses the delay between the user motion when the motion is displayed on the HMD to evaluate the visualization ability of the HMD. Accessing this metric is crucial as motion to photon latency integrates the hardware and software performance of the HMD into a single measure. It extends the results of the second test by qualifying the tracking system end-to-end latency, which is the true delay experienced by the user. To measure this latency, we have the robot travel along the same trajectory program for test 2. The chronicle is again used as the anatomical feature track to minimize the effect of positional error when trying to accelerate for tracking latency. However, we also defined a trigger point at each trajectory midpoint for which both the robot's Cartesian and effector pose and the VR HMDs reported, okay, and hand pose are known as level. That is, we have coordinates for a trigger point in both the robot and VR coordinate frames. Once the hand is seen to cross the trigger point, according to robots on reported forge, an LED ring on manipulator's wrist will be turned on. Once the VR HMD sees the hand crossing the trigger point and the entire HMD screen is colored purple. Similar the procedure used by Warburton. A high-speed camera on a smartphone was used to record the entire setup, including the robot's LED ring and HMD screen, to determine motion to photon latency. In our case, an iPhone 14 Plus iOS 17.6.1 mounted on tripod was used to record videos from this test as a resolution of 1080 into 1920 pixel and frame rate of 240 fps. The frame rate was validated manually using a microcontroller and LED, okay, leading us to determine the actual frame rate was 239.69 fps. This value was designed in our calculation. This value was used in our calculations. Following the test, videos were played back frame to frame from when robot's LED turned to when HMD screen turned purple. Counting the number of frames between these two events, dividing by the frame rate yields an estimate of motion to photon latency. Note the motion capture system was not used for this test. Instead, the robot's reporting of its kinematic state based on joint encoder feedback was used to determine the hand crossing of the trigger point. This method was selected because the robot's feedback rate is virtually latency free, that within 1 millisecond. Due to the real-time nature of robot's control loop, this improves our estimate of motion to photon latency. The results, now we will discussing the results. Test 1 results are for static performance. Data collection for test 1 resulted in 1176 total measurements. Unfortunately, 90 of these measurements were discarded as the HMDs could not successfully track the hand. Unsuccessful tracking was deemed if the hand was no longer registered within the virtual environment, or if the hand experienced abnormally high jitter while stationary. Static potential error for both Quest Pro and Quest 3 separated by anatomical feature conditions are displayed in figure 5. A two-way ANOVA examined the effect of HMD and anatomical features selected on the position error. There was a statistically significant interaction between the effects of HMD and anatomical feature selection on the positional error, F1 and 1741 and 8.686. Okay, and P is equal to 0.003. Simple main effect analysis showed that Quest Pro had significantly less static positional error than Quest 3, and their corresponding anatomical feature condition P is less than equal to 0.01. Okay. Results also showed that the clinical tracking condition on Quest 3 experienced significantly less error than the fingertip condition. The P is less than 0.001. But this was not the case between the Quest Pro tracking condition P is equal to 0.10. Mean result for the static positional error across test 1 condition are displayed in table 2. Okay, you can see the table 2, the Quest Pro fingertip, the Quest Pro conical, Quest 3 fingertip, and Quest 3 conical. Okay, you can see the static error and the jitter. Okay, fine. Jitter across HMD anatomical feature condition displayed in figure C. A two-way ANOVA examine the effect of HMD anatomical features is selected. Okay, on jitter, and statistical significant interaction was not found between the effects of HMD anatomical features selection on jitter. F1 1741 is equal to 2.542, P is equal to 0.11. This indicates that the influence of HMD on jitter is independent of the anatomical feature tracking condition. Simple main effects analysis showed that the Quest 3 significantly outperformed the Quest Pro in corresponding anatomical feature condition. I already read out it, I think so. Yeah, I think so. Lastly, in test 1, we examine the influence of hand rotation on both static positional error and jitter. A one-way ANOVA did not show statistical significant difference for jitter between the 7 test hand rotation. However, we did detect a significant difference in static error F66474 434 is equal to 2.902 and P equal to 0.009. A Tucky post-hoc test for error revealed no significant difference between groups, demonstrating that the effect size may be too small to make definitive claims for this result. The average result across the all position in testing region for each hand rotation are shown in table 3. So you can see test number 2, dynamic performance, significant three-way interaction between headset, vertical level, and anterior proximity of linear trajectory across all results in the second test were not found. Therefore, mean values across the testing volume are reported to produce results that provide an understanding of average performance within normal workspace of a user's hand. Okay, you can see here the table number 3, static positional error and jitter for each hand rotation evaluated in static test present as an average across the testing volume. Okay, you can see here the figure 7, this is table 4, this is table 3. Cold start CS latency, you can see static error jitter in this table 3, and Quest Pro 3 comparison Quest Pro and Quest 3. CS latency, CV latency, warm up duration, you can see MTP latency, cold start, CS latency, constant velocity latency, and motion prediction warm up duration in the dynamic test are shown for both HMD tests. Additionally, the motion to photon MTP latency from test 3 is presented. All results are presented as average across the testing volume of the two HMDs. Okay, so figure 7 displays an example trajectory as recorded by the Quest Pro's markerless hand tracking and motion capture system ground truth. The plots also visualize latency development across a trajectory as the motion prediction within the tracking algorithm passes its warm-up duration. A two-sided t-test failed to reveal any significant differences between average cold start latency and warm-up duration and constant velocity latency of the Meta Quest Pro and Quest 3. These results are displayed in table 4. So now for test 3, motion to photon latency, a two-sided t-test of motion to photon latency of the Quest Pro, Meta Quest Pro and Quest 3 did not reveal any significant differences. The motion to photon latency, the motion to photon test results are displayed in table 4. I have already showed you the table, this table 4. Okay, cold start CS latency and constant velocity CV latency, and you can see here warm-up durations and MTP latency also. Okay, for both the Quest Pro and Quest 3. Discussion. So discussion is going to start. Work by Abdul Karim represents to the author's knowledge the only other characterization of markerless hand tracking on commercial HMDs. While their study provided a foundational framework for hand tracking characterization, we aim to provide a more comprehensive dataset. Matrices considered in one considered a single average value for latency, as discussed earlier, and again supported by the results in this study. It appears that a single latency value is insufficient to understand how tracking performance develops over a trajectory. This motivated the inclusion of multiple evaluation for latency within our characterization, included in our second and third test, to provide sufficient uh, information on markerless hand tracking. A benefit of the prior framework was the target reaching tasks to evaluate static positional accuracy. This test was evaluated the hand tracking performance across a testing volume, which produces produced results that showed performance. Uh, a testing volume performance dependence on proximity to the HMD. This task provided direct motivation for developing the testing volume within this study and ensured spatial performance was properly considered within our framework. It is clear from the results of test 1 as shown in figure 5 and figure 6, and tracking performance under all the test conditions depends on the proximity to the headset, as all HMDs have cameras with fixed field of view identifying volume that elicit strong tracking can help VR designers develop proper interaction in the virtual environment. Okay, fine. Now it's time for the starting from this position number 5. Refer to figure 4. You can see a lot of things. Okay, so you can see the position number 5 here. Okay, so position number 5, refer to figure 4. This is not figure 4, this is figure 4. Okay, this is, where is figure 4? Okay, this is a figure 4. Static performance testing user for each level using test 1. Okay, so figure 7, where the figure position 5, referred to figure 4, generally delivers the first performance as it was further lateral point along the first anterior layer. This positioned the hand in an awkward position relative to the HMD and served as a blind spot that occasionally experienced drops in tracking. Okay, the best tracking was found in position with small lateral and small vertical deviation from the headset. Okay, you can see here, and in second vertical level, this was expected due to the orientation of the cameras being positioned with a forward facing field of view and likeness that most of the training data for the hand tracking algorithm were captured in similar positions, as these are the positions a user's hand most often occupies. The test 1 also demonstrated that the superior performance experienced in the canonical tracking conditions compared to the corresponding fingertip condition, as the fingertip has a higher likelihood of being victim to self-occlusion experienced by the hand. The tracking algorithm must make prediction of fingertip location with less information during these instances, which would lead to worse performance. The results align with this rationale, which enforces the canonical as the superior tracking location out of the two anatomical features tested. While accurate fingertip tracking is crucial for tasks like fingertip-based user interaction in VR. This finding underscores the canonical greatest reliability as a tracking feature, making it preferable for general purposes such as hand pose identification. Combining the result of the study with the work of Abdulkam, the hand tracking performance of the past 3 iterations of MetaQuest HMDs can be compared. The average static fingertip positional error of the MetaQuest 2 was shown to be 1.1 centimeter. The average result for our fingertips condition were 2.05 centimeter and 1.30 centimeter for the MetaQuest 3 and MetaQuest Pro, respectively. While our results shows a greater average at a face value, test 1 records measurements while the hand is at 7 different rotations for each positions within the testing volume. By rotating the hand out of the standard palm down configuration, which was standard for the MetaQuest 2 evolution, the tracking difficulty increases due to the potential for self-occlusion and or reduce surface area for the HMD cameras perspective. The results within this study present a better evaluation of general tracking performance as both spatial and rotational conditions were considered. With respect to the rotational conditions, performance was best when the hand was in palm down configuration. Rotation 1 and 3. The pronations, pronation and supination condition for of rotation sections, rotation 7 produces the worst performance. This was likely due to the hand surface area drastically decreasing from the perspective of the HMD as the hand rotated along its anterior axis. As natural hand interactions rarely occur in a palm down configuration, decreased tracking performance should be accounted for when designing interaction that differ from this ideal state. Initially proposed by Warburton, our results confirm that multiple latency results are required to fully evaluate tracking latency. This is evident by the dramatic difference between the cold start and constant velocity latency values. The cold start latency results evaluate tracking performance under worst case condition as the motion prediction effects of tracking algorithms are mitigated. The average cold start latency results of 229.2 millisecond and 220.5 millisecond for the MetaQuest Pro and MetaQuest 3 respectively are above the previously mentioned discernible threshold for visual latency as measured in 15 and 17. So you can see this demonstrates that the starting point of trajectories or hand motions with abrupt acceleration can experience latency that the user may detect. This could affect user experience, and hand motions with low acceleration should be desired when designing hand interaction within a virtual experience. The constant velocity results drop below the mentioned discernible visual threshold for latency, which demonstrate the importance of motion prediction within hand tracking algorithm on MetaQuest HMDs and warm-up duration for motion prediction. Okay, you can see here. Is a key result of understand how quickly peak tracking performance can be reached as during constant velocity motion. This warm-up period represents the transient state of tracking performance, and again must be considered when relying on markerless hand tracking data for application requiring precise tracking. Since the warm-up duration results for both HMDs denote significantly different results, it is likely Meta is using the same predictive algorithm on each HMD. The motion to photon latency results of the final test represent the best indicator of complete system performance within the study, as it encompasses both the hand tracking and visualization performance on the HMDs. The results of 33.20 millisecond and 38.33 millisecond for the MetaQuest Pro and MetaQuest 3 respectively. Okay, you can see the difference. Below the discriminable thresholds of 50 millisecond and 90 millisecond discussed before. It must be noted that the 50 millisecond threshold for visual reception is breached for the results of both headset through one standard deviation is considered. This demonstrates that although the average performance of the markerless hand tracking on the Meta HMDs may be sufficient to enable a positive user experience, discernible effects produced by system latency will be common, which may have a negligible implication. Okay, while this works aim to provide an extensive framework for markerless hand tracking characterization, limitation present opportunity for future work across the three tests. The testing volume only considered positions and trajectory located below the HMDs, as most hand tracking head interaction occur below the eye line. Testing volume are defined to best match those locations. As virtual experiences become more complex and potentially demand more from a markerless hand tracking or VR system, characterization across a large volume may be required to facilitate new interaction. Also, the test condition within this work only involve single joint tracking, and did not evaluate the tracking of more macro features such as finger angles or hand path. Okay, this evaluation is also limited to a single static hand model. This limitation may affect the generality of the results, and future studies could explore variation in hand shapes to address this issue. Many traditional tracking conditions exist that would increase the depth of analysis provided by the results of this study. So conclusions are markerless hand tracking represent a key development pathway for improving future virtual experiences. This technology currently being standard on many commercial HMDs demonstrates a push to facilitate virtual interaction with natural hand manipulation while implementing hand tracking in virtual experiences is an important step forward. Consistent and ongoing evolution are necessary to properly characterize and document the progress of this technology for applications. Okay, so you can see here requiring accurate and applications requiring accurate and precise hand pose data. This has motivated us to develop a repeatable and extensible process for markerless hand tracking characterization within this work to not only facilitate the evolution of current commercial HMDs but also to lay the foundation for future testing and comparison. Our work represents to our knowledge the first use of robotic to characterize markerless hand tracking performance. Doing so allows for systematic, precise, and comparable characterization of markerless hand tracking on VR system. The methodology outlined in this work produce results of positional accuracy, GTR, and latency. This methodology was applied to two commercially available VR HMDs, the MetaQuest Pro and MetaQuest 3 HMDs. Okay, in best performing conditions, tracking control, the MetaQuest Pro outperformed the MetaQuest 3 with respect to positional error 1.22 cm and 1.73 cm respectively. The opposite was true for jitter, that is 1.77 cm and 1.11 cm respectively. The effect of hand proximity to HMD on positional accuracy and jitter was evaluated, and weaker performance was observed as the hand moved to the periphery for both matrices. Latency results were also highly variable for MetaQuest Pro, 15.8 to 229.2 millisecond, and Quest 3 14.4 to 220.5 millisecond. While the characterization framework developed in this work is comprehensive and the analysis was completed across a limited volume, only points below the eye line of the HMD were tested. And constraints imposed by the manipulator limited the overall testing workspace. Now, the future work can grow the knowledge developed within this work by expanding the testing volume of future characterization and evaluating the markerless hand tracking performance of other commercial VR HMDs. So acknowledgements you can give. This work was supported by Natural Sciences Engineering Research Council of Canada and Connected Minds CFREF program. You can see the reference URL www.euroco.ca research connected minds. Okay, you can see the references that is given. Thank you so much for reading this paper with me. Now it's time to summarize it. Okay, we have a summary of this paper. Summary of I'm going to discuss the summary now. First, going to start 1 minute. It's 1 hour already, so I will not take so much time. I will go search here notebook LM notebook. I will search for notebook LM. Okay, and just click here notebook LM, Google notebook LM. It is opening now. Let it open. I think the screen is rotated now. I think I should stop it because some issue will be there. So summarizing in this paper, I am going to summarize the paper: Robotic Characterisation of Markerless Hand Tracking on MetaQuest Pro and Quest 3 virtual reality headsets. So this paper represents a systematic evolution of hand tracking performance. Okay, on commercial mixed reality devices, recognizing the lack of standardized performance data for markerless hand tracking. The researchers developed a methodology using a robotic manipulator to precisely measure positional accuracy, jitter, and latency. Key findings that are given in this paper was: first, the methodology. The study utilized a robotic arm to provide highly repeatable movements, allowing for standardized characterization framework. Okay, this is very important. And tracking feature. Performance was influenced by specific joint being tracked. Both the Quest Pro and Quest 3 showed the lower error and jitter when tracking the knuckle compared to fingertip. Okay, so hence comparison, headset comparison, the positional accuracy. The Quest Pro achieved better average accuracy. It is 1.22 cm error. Then Quest 3 1.73 cm error in best condition. Okay, the jitter. The Quest 3 exhibited less jitter, 1.1 centimeter, and Quest Pro 1.77 centimeter. That's the jitter difference. Okay. The latency was found to be highly variable for both devices, ranging from approximately 14 and 15 millisecond to over 200 millisecond. Okay, the factor influencing performance. The results highlighted that proximity to the headset, hand rotation, and the selected joint all significantly impact tracking quality. Okay, the relevant questions and answers that can be asked on this paper are: why did researchers use a robotic manipulator for this study? Why they use the robotic manipulator? Why they use another manipulator that available in the market? The reason why the robotic manipulator was used to create a standardized characterization framework that allows for highly systematic and repeatable measurements of positional accuracy, jitter, and latency, which is difficult to achieve with human subjects. Okay, which joint is more reliably tracked by these headsets, the knuckle or the fingertip? Definitely the fingertip. According to the study, tracking error and jitter were the lowest. Tracking error and jitter were lowest when the knuckle was tracking point, and compared to fingertip for both Quest Pro and Quest 3. Okay, knuckle. Okay, how do the Quest Pro and Quest 3 compare in terms of jitter? And the Quest 3 perform better. Quest 3 perform better regarding jitter with a measurement of 1.1 centimeter, while the Quest Pro showed a high jitter of 1.77 centimeter. What is the range of latency observed during the testing of this headset? A latency of highly variable for both. The Quest Pro runs from 15.8 to 229.2 millisecond, and Quest 3 runs from 42.4 to 220.5 millisecond. So you can see here, you can ask other question also by clicking this. Just by clicking this, suppose how does hand rotation affect tracking accuracy? I can ask this. Any question you want to ask, you can ask. You can get detailed information from this by it was search from the paper that is already provided into it, and from that it will give the answer and all the relevant questions you can produce and with the answers by using this great tool. Okay, you can use. So I asked the question: how does hand rotation affect tracking accuracy? The hand rotation is identified as one of the key factors that significantly influences the performance of markerless hand tracking on both MetaQuest Pro and Quest 3. According to the research that given, hand rotation along with the hand proximity to the headset specific joint being tracked, such as knuckle versus the fingertip, directly impacts tracking accuracy and jitter, while the provided abstract confirms that rotation is a critical variable in the performance measurements. It does not detail the specific degree of rotation or exact numerical increase in error caused by different orientation. The study uses a robotic manipulator to systematically test these variables, provide a repeatable framework to measure how these physical changes like rotating the hand affects the system ability to maintain a precise lock on the joints. If you okay, fine, it's okay. So it's time to end this video now. Thank you so much. If you want to read, I will provide the link of this paper. You can go to link and read this paper by yourself, and this is very interesting paper, very informative paper. Please read it, and if you have liked this video, please subscribe my channel also and share this video with your friends. And I'm doing a lot of effort. Please help me to support. Okay, thank you so much.